Welcome to Ada Core University. My name is Quentin Oshem, and today I'm going to introduce to you the notion of arrays in Ada. If we look back at the type model chart that we discussed earlier, we can see that so far we've only been talking about elementary types, namely enumeration, integers, and floating point values. We are now going to start working on composite types, that is to say types that are composed of several values. The simplest kind of composite type is the array, which is going to be today's discussion. The first interesting thing about arrays in Ada is that they are first-class citizens. An array is an actual construction of the language associated with properties, and it is not equivalent to a pointer as it would be with C or C++. Ada being a strongly typed language, all arrays need to be typed. So in this example here, the first thing that I'm doing is to create a type for the array, and only once I have this type can I declare a variable. In order to create or to define an array type, I will have to provide two pieces of information. First of all, the way the array is going to be indexed, what is the form of the boundaries, and second of all, obviously, the component type itself. So if you look at the example here, T is an array indexed by integer, and I'm not providing any specific range, and it contains integer. And after that, I have A, which is an instance of T, with specific boundaries for 0 to 14. Regarding the components of the array, what is important to understand is that these components have to be a definite type. That means that we know the size of the object that is going to be put in the array. It's quite different from languages such as Java, where everything is a reference and you can have any type as a component of the array. In Ada, you will need to make sure that the size of the type is known at compile time, otherwise the compiler will refuse to compile the type. The array type itself can be definite or indefinite. In the first example that we saw, I said that the size of the array, the boundaries, was not given at type definition, which means that the actual size of the array will be known where creating a variable and may vary from one instance to the other. This type is indefinite. I do not know the size just by looking at the type. But it is possible to say that an array is constrained always within the same boundaries. So in the example on the slide, you can see two type definitions. One is definite. It's an array indexed by integer, which boundaries are always 1 to 10. The second type is indefinite, and I'm using this diamond notation to specify that the range is unknown. In Ada, we would say box. Then at variable declaration, I do not need to provide any additional boundary information when instantiating a definite type, because the boundaries are already known, which is why here A1 definite doesn't require any additional information. When declaring A2, however, since I do not have yet the actual boundaries of the type, I need to provide them explicitly. Here I'm saying 1 to 20. The indexes of an array can be of any discrete type, which includes integer and enumeration. So for example, it is possible to index an array after character, after boolean, or after any custom enumeration that you may have in the program. The indexes have to be defined on a continuous range, which may be empty. If you look at the first box, for example here, you can see 4 different array types declaration with different indexes, all of them containing integer. The first one is one that we saw already. A1 is an array indexed by integer, and I don't provide any specific boundaries for the type. A2 is an array indexed by character, and in this case I have provided specific boundaries from character A to character Z. A3 is an array indexed by integer, and its range goes from 1 to 0. As with loops, as we saw in the previous set of slides, ranges always have to be given in growing order. So the fact that 0 is smaller than 1 means that this range is empty. So A3 is an empty array. This may be weird just looking at it right now, and the use of such array may not be obvious. However, range can be computed dynamically, and in this case it's very handy to be able to define dynamically an empty range. The last type, A4, is an array indexed by Boolean. And as you can see in this very example, I did not provide any explicit range to this array. This means that A4 is a definite type, indexed from Boolean tick first up until Boolean tick last. So here that's a 2-element array. In case of an array which boundaries are dynamically computed, for example here I'm computing the range depending on a variable, then the size is only computed once at the point of the array type declaration. And if there are further changes to one of the components that is being used to compute the range, that will have no impact on the array declaration that happened earlier. Arrays components can be directly accessed if you have an index. So, for instance, here V is an array from 1 to 10. I'm accessing the element 1 of V and putting 0 to it. Arrays have specific attributes that allow to extract the length, the range of indexes, the first index, and the last index, which are accessed through length, range, first, and last attributes. One important point that is different from languages such as C is that there are dynamic checks on array access. So on the second example here, I'm trying to access to the element 0 of an array that is constrained from 1 to 10. This will be checked at runtime, and the program will raise an exception on this very line of code. Ada provides some unique primitive capabilities to arrays, allowing them to be manipulated very easily in the program and in a very intuitive way. The first one is copy. When an array is assigned to another array, here A2 is assigned to an A1, Ada will perform an element-by-element copy. This is different from a reference copy or pointer copy that may happen in other languages. Here, A1 and A2 remain two separate arrays, which values are copied one to the other. The requirement for such copy to work is that the length of the two arrays are equal. If the indexes are different, that won't be a problem, and the values of the source array will slide to the value of the destination array to be aligned. So if we look at the second example, I have three arrays, A1, A2, and A3. A1 has 10 elements from 1 to 10. A2 has 10 elements from 11 to 20. And A3 has 20 elements from 1 to 20. It is okay to assign A2 into A1, and object of A2 will slide to match the position of A1. So for example, the element 11 of A2 will be copied to the element 1 of A1. However, it will not be possible to copy A3 into A1 because I would be trying to copy a 20 element array into a 10 element array. This will raise an exception at runtime. It is possible to initialize an array after the value of another array. In this case, the rules that we just saw in terms of consistency between the source and the destination, mainly the fact that the length of source and destination needs to be the same, will apply. If the boundaries of an array are not specified on declaration, but this array is explicitly initialized after another array, then the boundaries of this new array will be automatically deduced from the initialization expression. So in the second example here, I'm saying that A2 is of type T, and I don't provide explicit boundaries. It should not be possible to do that because T is indefinite. However, because I am providing an initialization expression, I know the boundaries of this expression. Those are the ones of A1, and therefore I will copy those boundaries in A2. A2 will be an array from 1 to 10 initialized after the values of A1. Let's talk further about the array native capabilities. Slicing is a way to retrieve a portion of the components of the array. It is very useful when you need to work only on a subset of the array element without having to create a new array or a new structure. A typical example of that is when doing an array copy. Here I have A1 and A2 which are of different size. A1 has 10 elements, A2 has 20 elements. So I cannot copy A2 into A1. However, I can specify that I want to copy a portion of A2 within A1 and ensure that this portion of A2 will match the size of A1. For doing that, I'm opening a parenthesis after the array reference and then providing the range of value that I want to extract from this array. So now the assignment will work. I'm assigning the 10 first element of A2 into the 10 elements of A1. On the next line, I want to only work on a subset of A1 and assign a subset of A2 within a subset of A1. What I'm saying here is that I want to assign the elements 5 to 7 of A2 into the elements 2 to 4 of A1. Ada provides a quite extensive way for defining values for an array, or literals. An array literal is a way to define the various components or the various indexes that we want to put in an array. For example, here, the first literal that you can see is a literal of 3 elements, 1, 2, and 3. That's called the positional notation. This aggregate here is finite. I know its size, it's 3. Note that I do not know the values for the indexes here. So AIDA will generate those automatically and start with the smallest index in the corresponding array. It is possible to fix the indexes when creating an aggregate. So in this second example, I'm saying that I have an element 1 at index 1, an element 10 at index 2, and an element 30 at index 3. So the only difference between those two forms is that in the second one, I specified the indexes for each element. But this is still a finite array. I know the size of it, it's 3 elements. The third example introduces a new notation, others. What I'm saying here is that the first element is 1, and then all the others elements of that array are being assigned to 0. Now we may have a problem here, is that all the others elements mean that I need to be able to enumerate those elements. So this form of aggregate can only be used within a context where I know the expected size of the array through other means, and we'll see an example of that. The point is that this aggregate is indefinite. I do not know its size outside the context. The fourth form is very similar to the previous one, but instead of just saying that the first element is 1, I'm saying that this first element is at index 1. I am using the name notation for an indefinite aggregate. Now I can use those aggregates in any place where an array value is expected. Parameter passing, assignment, initialization, etc., etc. The constraint is that if I want to use an indefinite array, I know from the context the size of the object. So looking at the second box of example, I have an array T which contains integer and is indexed by integer. The array T, the type, is indefinite, so it needs to be constrained by the declaration. V1 is of type T, and I'm not providing any explicit boundaries for T. But thankfully, I am doing an initialization. The initialization is done through an aggregate, which is of 3 elements, 1, 2, and 3. So because I'm doing this initialization with an array, I'm going to deduce the boundaries from the initialization. Here, V1 will be of 3 elements, and the first index will be integer tick first. Now, on the second case, V2 of T, which is initialized by an aggregate mentioning others. What I'm saying here is that all of the others elements of the aggregate are initialized to 0. But how many is that? In V2 of T, I haven't specified any size. In the aggregate itself, I haven't specified any size either. So I have no means to know the size of the aggregate, no means to know the size of the array. That's going to be refused by the compiler. This is only because I'm on an initialization. What I could have done is to specify boundaries at the variable declaration. With assignments, however, everything is clear and fixed. If I say v1 equals an aggregate which is written others take 0, I know that v1 has 3 elements. So I can deduce from this context that the aggregate needs to have 3 elements, and the compiler will indeed generate an aggregate of 3 zeros here. Arrays are associated with the native concatenation notation, which is the ampersand. So I can concatenate any array. As we will see later on, of course, that's extremely useful for strings. But any array can be subject to concatenation. the lower bound of the resulting concatenation will be the lower bound of the left operand. So here, for example, I have A1 and A2, which are arrays of 3 elements. I can create a new array of 6 elements concatenating those 2 objects. And then what I do is that I'm assigning A3 after the value of the result of this concatenation. It is possible to concatenate an array with the value as well. In this second example, A2 is an array of 5 elements, 1, 2, 3, 4, and 5. The native array equality will compare element one by one and will return true if the size of the true array is equal and all the elements are equal as well. Let's now have a look on how to iterate over the components on an array. The first loop, for in, allows to iterate over the range of the array indexes. So if I write for I in a tick range, I'm saying for I iterating over all the indexes of the A array loop, and then I can manipulate this index within the loop. In a lot of cases, we don't really care about the actual indexes. The thing that we are trying to loop over are the actual components on the array. In Ada, there's a loop that does specifically this, which is the for of loop. So if I say for v of a loop, I'm saying please iterate over all the components of a and put the value of this component in v. It's actually a bit more than a value here. It is a reference, which means that if I modify v within the loop, I will modify the actual component from within the array. So far we've seen one-dimension arrays. It is possible to create several dimension arrays, which are matrices. In the screen you have an example of the syntax. You would enumerate the various indexes within the index definition of the array. The first, last, and range attributes will work and will require to have the dimension that is being looked at in parameter. One other way of declaring matrices is to use arrays of arrays. So in this second example, I have T2, which is an array of type T1. What makes this method more complex is that since I'm containing definite object, I need to fix the size of the contained array at the second type declaration. While on the first case, I can have both boundaries to be unconstrained. As for many other languages, strings are special kinds of array. There is a standard string definition in Ada, which is an array indexed by positive, which means that the lower bound cannot be lower than 1, and which obviously contains characters. There is a special string literal for array, which is written by quotes, and we provide an ASCII package as well for specific character values. One important point here, and one interesting difference with C, for example, is that in Ada an array is associated with boundaries. So we don't need to have a terminating character, like the null character. However, in a number of cases in particular, where interfacing with other environments, this null character may have to be added. And the last example here shows specifically how to do that. one last bit of information. It may be interesting to force an array to be receiving a given value in the absence of an explicit initialization. This is possible using an ADA aspect, default component value, which will force an initialization at a given value. The one restriction of this default component value aspect is that the value that is provided has to be known at compile time for performances reason. We say that the expression of this aspect has to be static. Let's now verify your understanding. For this question and the next, if you think there are no errors in the code, click on the green icon next to yes. If you think there are errors, click on the corresponding location in the code. In either case, once you are sure of your choice, click on Submit. Everything is fine here. The fact that there is no specific range associated to the array type definition T means that the full range of the index type will be taken. So T is of a definite size, going from 1 to 10, as that is the myInt type definition. And indeed, v of 1 equal 2 is appropriate, since 1 is within the 1 to 10 range. This is an interesting case. The type definition is okay here, but what I'm saying is that T is an array type indexed by integer, and because at the type definition I'm not specifying any range, the default will be going from the first value of integer to the last value of integer, which is about 4 billion elements on a 32-bit machine, which is quite large. So as soon as I declare a variable v of type t here, I'm going to reserve a huge amount of memory in the system on the stack, and that will not be possible. So this will be a problem either at runtime or possibly at link time, depending where this variable is declared. Another interesting surprising case. T1 and T2 look the same. They are both indexed by integer, they are both indefinite, and they both contain integer. So from a structural point of view, v1 of type T1 and v2 of type T2 are pretty close. On top of that, both of them are of 3 elements. So from a structural point of view, it could make sense to assign v2 into v1. But Ada is a strongly typed language, and from the Ada point of view, at the semantic level, T1 and T2 are two separate types. They have nothing to do together. So the assignment from v2 to v1 is forbidden, because v1 and v2 are not of the same type. This is a very common mistake when coming to Ada. As you have seen in the previous slides, it's quite difficult to make assumptions on the actual boundaries of an array without seeing the declaration. In this case, T is an array type indexed by integer and containing integers, and V of type T is initialized after an aggregate of 3 elements. In the aggregate itself, I am not defining any index, So the ADA semantic states that the first index of the array will be the first possible value of the index type. In this case, integer tick first. So something around -2 billion and something. As a result, V has 3 elements indexed at -2 billion something, -2 billion something plus 1, and then plus 2. There is no 0, 1, or 2 indexes for this V array. Therefore, the accesses that I'm making in this computation are wrong and will raise a constraint error. Everything is fine here. Although V1 and V2 have different indexes, the length of the two arrays is the same, the type is the same, so as a result of the assignment, V1 at position 1 would be equal to V2 at position 10, and V1 at position 2 would be equal to V2 at position 11. Remember that a type is only elaborated at one point on its definition, and that's the only place where the indexes for the type are computed. They are not recomputed afterwards. So here I have a type which is going to be constrained within 1 to 10, because at the time of the elaboration of the type, at the time of the creation of the type, x equals 10. Later on, I am modifying the value of x, but this has no impact over t definition. So when I declare v2 of type t still contains 10 elements from 1 to 10, and therefore the assignment is correct. This is another example of making wrong assumption on the boundaries of a type. V1 is constrained between 1 to 3. So the first index of V1 is 1. That's specifically what is said here. However, V2 doesn't have explicit boundaries. It's initialized through an aggregate that does not define any index. Therefore, it will be indexed from the first value of integer, and this means that this first index will be around -2 billion. In the loop, I'm iterating over the indexes of V1. That's not too bad. What I'm saying here is that I can't make any assumption on the actual indexes of V1, so I'm using the range attribute to iterate over its range, whatever that might be. However, I'm then referring to V2 of I coming from the range of V1, so I'm assuming that the range of V1 is equal to the range of V2. And although those two variables are of the same size, the indexes are different, and I will raise an exception here. Type T is given an explicit range from 1 to 10. So this type is definite. It's fixed. Its size is of 10 elements, boundaries from 1 to 10, and that cannot be changed. As a result, it is not possible to add extra boundaries when declaring a variable of this type. Here, I'm trying to say that the variable v is of type t constrained between 2 and 9, while it's not possible to change the size of the value of the type anymore. This is a very frustrating implication of the ADA model. A string is an indefinite type. I do not know the size of the string, but for the components of an array, I need a definite type. So this declaration here is incorrect, I can't just create an array of strings like that, which is quite annoying. There are other ways to create container of strings. We can create a pointer to string of the component. We can use the embodied string type. We could even provide a constraint for all of the string of this array. So depending on the context, the workaround might vary, but this very declaration is incorrect. Remember that default component value needs to refer to a static expression for performances reasons. We haven't seen all the details of static expressions yet. There are very precise definitions of what should be considered a static expression by the compiler. But for the purpose of our example here, let's just say that a static expression is an expression that must be known at compile time, systematically. Here, x is a variable, so I can't know its value at compile time. I need to execute the code and look at the actual value of x before knowing anything. Therefore, this declaration will raise a compilation error, x not being a static expression. This concludes this section on array types. Thank you very much for having followed in. Please stay tuned, there is a lot of interesting topics to come.